from yesterday on state space. Today we started chapter 4 as well, and we just finished the definitions of poles and zeros. We're good. All right. Every week the class shrinks a little bit. Yeah. Yeah, I'll do a short overview just because yeah, we just started on it. So basically, poles and zeros is defined as, let's just go to the definitions. So when we have a transfer function g, poles are basically values of s that make g go to infinity. So the way I think about it is you find the roots of the denominator, and then zeros are the roots of the numerator that make g go to 0. So basically the roots of the numerator that are the zeros. Those are the definitions set by in chapter 4. Uh, Basically, but what that tells us is poles tells us the stability of our system. If you have one positive pole, that's one positive pole is all it takes for your system to go unstable. For it to be stable, you need to have all the poles to have negative real parts. If your pole is purely imaginary, meaning that it's neither positive or negative, it actually is called marginally stable, but you can only have one. Well, yeah, it's just marginally stable. There's a special case where it's not, where it grows unbounded, but we won't focus on that until maybe later on in this chapter. So basically know that negative real poles are stable, positive real poles are unstable. Uh, and then zeros will actually tell you basically how a system, if it's going to respond faster, if it's going to respond opposite to what you think it will do. So like a positive zero, what it does is if I put a input and there's a positive 0 in the system, it's going to go opposite to my command. So it sounds counterintuitive, but maybe think of, so vertical takeoff airplanes that can take off vertically, those have a positive 0, where if you tell it the thrusters to go left, it's actually going to go right. So they counteract that. It's going to go left initially, then go right. When you go on your bicycle riding, like, have you ever heard of counter steering, where you push right to go right, you don't pull right? And maybe you haven't noticed, but you do this subconsciously if you know how to ride a bike, and you might not notice at all. So what happens is if I tell it to go right, it's going to initially go left because the steering turns left, but then it tips right. So that's a system that has a positive 0. Systems with negative zeros don't really affect too much the direction of or doesn't really affect the direction of your input based off of the output, but it will affect, I guess, like the size of your output. Basically, zeros affect the amplitude of your output. We'll do some derivations which prove that. But I think the most important part in this section here is just knowing what poles are first, because poles will indicate your stability. That's what we're focused on. Zeros, it's a little bit more nuanced and less intuitive, unfortunately. Okay, so we went over the definitions, and then we're at this point where the way poles are tied into eigenvalues, basically poles are the eigenvalues of A from our state space. And the system is asymptotically stable if and only if all the poles have negative parts. So all of them have to have negative parts. If you have a single pole that is positive, or a single pole that is imaginary only, it's no longer asymptotically stable. It's just marginally stable. And we'll go over those definitions formally in chapter 6. Asymptotically stable means that it's a global minimum, so it'll converge to that global minimum, usually at 0 or at the origin. Let's see. Let me pull up my notes. Okay. Oh, and then one thing about the eigenvalues of A, you can find the pole. So instead of finding the transfer function, if you have the A matrix only, that's all you need to find the poles. And to do that, you can find poles, find the poles by solving the characteristic equation. The characteristic equation, which is determinant of your S multiplied by your identity matrix minus A is equal to 0. So when you solve for that, that's going to be your eigenvalues as well, and those are your poles. And basically, if we look at this here, G of S is going to be equal to N of S divided by determinant of Si minus A. That's the relationship. That's how they're correlated. One other thing about poles and zeros is that you do want to include any pole zero cancellation. So let's say if I have G of S is equal to S plus 1 over S plus 1 times S plus 3, we want to include it, pole zero cancellation. It might seem very redundant right now, but in reality, zeros and poles are never going to be the same exact value. Sometimes they might be S plus 1.00001, and then the pole is going to be S plus 1.00005. It's not exact pole zero cancellation. So in reality, in real systems, you'll rarely get pole zero cancellation. You want to include that. So then if I ask you what the poles and zeros are, you just say 0 is -1, poles it's -1 and -3. Okay, so then if we were to find the poles and zeros here, we have different examples. First one's like the easiest one. We have for our zeros. What are our zeros? Anyone? Yep, -1 and -3, right? And then we also have a second -3. So I actually like to write it out multiple times. Instead of, -1, -3 implies that there are 2 poles. I write it like that. So there are 3 zeros. And then for poles, it's going to be -1. So we include the pole zero cancellation. Be careful with this on exams. I have done factorization for people, and people will say the pole is at -1 minus j and -1 plus j. Be careful with that. It's actually going to be +1 minus j for, if I call this 1 and 2, it's going to be, this is for 1, and then it's +1 plus j. Just be extra careful with signs. That's a very common error on exams. It seems obvious now, but under the pressure of exams, you're so used to seeing or working a certain way. I used to have problems where it's like you almost always have negative poles. So that then on exams, when I throw in a positive pole, people still put a negative pole. So just be careful with the signs. Note that these two are also called complex conjugates. They're conjugates of each other. With transfer functions, you'll never get a single imaginary pole or zero. You'll always get them in pairs, so you'll always get conjugates. Okay, so for the second one, find the poles for the state space. The B matrix here is unnecessary. We don't need it. I just threw it in there just because sometimes I'll give you extra information that you don't need. All you need is this. Determinant of Si minus A is equal to 0. And you solve for that, you get your poles. So let's do that. Determinant of your identity matrix 1, 0, 0, 1 minus your A matrix 0, 1, 2, 2. That's equal to determinant of, oh, it should be S here. Determinant of S minus 1 minus 2, and then S minus 2 is equal to 0. So then we get S squared minus 2S minus 2 is equal to 0. And then when I solve for the roots here, S is equal to minus 0.732, and I have a positive pole at 2.732. So this system is unstable because it has a single positive pole. So whenever I ask you about poles, I want you to be thinking about stability, right? Is it stable? Is it unstable? And this is unstable due to a positive pole. So we can have 100 negative poles, but if we have one positive pole, it's unstable. Does not matter. Any questions so far?
So we didn't have to use the B vector for finding the poles, right?
Okay. Now the last one, if we give you a differential equation where X is the output, U is the input, and I tell you to assume 0 initial conditions, what we can do here is we can just take the Laplace transform and find the transfer function, or we can take the, or we can, question is, we didn't have to use the B vector for finding the poles, right? Yes, that is correct. We do not need the B vector. We don't even need the C or D matrices either. Okay, so this last one, there's two methods to find the poles. One is taking the Laplace transform. We get the transfer function, and then from there we can find the solve for the denominator is equal to 0. Second method is using state space method, where we get the A matrix, and then we take determinant of Si minus A is equal to 0. So these two are the same. There's different ways of solving it. It's whichever method you feel the most comfortable with. So let's do method 1. If I take the Laplace transform of x double dot plus 2x dot plus 1 is equal to 2u dot. The Laplace transform of a double derivative is s squared times x of s. Then we have the derivative, the initial condition of the derivative minus the initial condition of the position. Yeah, question. Okay. Obviously, I don't quite understand the difference. Like, it might not be relevant here, but is the state space like a Eulerian formulation, or am I misapplying? So Lagrangian, is that from 588 right now? Oh man, it's been a while since I've taken that class. That method of using stability, I think, is based off of how energy flows. Or, yeah, and the way you do it, and this is getting very, very ahead. It's not even covered in this class. I think it's like if you define your function v of x, and x is your state, and then you have some matrix x multiplied by PEX, and this is just your function. I think you get that from, is a positive definite function. This is a quadratic, so it looks like a bowl. And let's say if I take, but we don't know if it looks like that or if it looks like that. Well, actually, we know that it looks like this because it's a positive definite matrix. If we were to take the derivative and this is negative, that means that our bowl will always force this to a lower energy state, meaning it's stable. It doesn't have to do with state space though. So I think that's just a different way of yeah, and what you're thinking of, I think it's very similar to Lyapunov stability, if you're ever interested. That's actually how they do nonlinear analysis for stability of maybe I'll just for this is for nonlinear systems. Yeah, that's actually the primary, or not primary, but that's one of the ways. So it's not necessary for this class, but I don't exactly remember. The way you find P, you do use your state space. And I don't remember it's the same as Lagrangian. I think it's similar method. Yeah. Yeah, no problem. Anyway, so when I take the Laplace transform of that, you get s squared times x of s plus s times x of s minus the derivative minus the position at the initial condition, which is 0. When you take the Laplace transform of a constant, it stays a constant. So it's just plus 1 is equal to s times u of s minus the initial condition of the position, or not the position of the input. Okay, so then there's this one here, which seems like it's kind of messing things up, but don't worry about it right now. Let's pull out the x of s, and we get s squared plus s is equal to s times u of s minus 1. Divide both sides by this s squared plus s. I'm going to pull out the yeah, it is 2s. Thank you. All right. And then this should be a 2s here and 2s u of s. All right, so then we get 2s over s plus 2 multiplied by u of s minus 1 divided by s times s plus 2. All right. So the reason why I tell you not to worry about that constant there is because when we look at the definition of the transfer function, we only account for the input response, which is this. Yeah, I'll use a different color because that one is yellow. We'll use blue here so we can see that this is different. This is our transfer function. This is our transfer function. And this one here, it's kind of like it's similar to the natural response, but I did say it assumes 0 initial conditions. This is similar to the natural response. It's basically a initial condition that I impose onto this differential equation. Like, for instance, if I were to say x of t is equal to 1 or something like that, right? The reason why I say not to worry about it is just because think of this one as an offset. What's going to happen is that we're going to just have this whole response just offset, not by 1. It's going to be offset by some amount because when we do partial fraction expansion of this term here is going to be a over s plus b over s plus 2. And the offset's going to be by some amount of a. This is an offset. And the reason why we don't even care is because if you look, this transfer function actually shares the same poles as the natural response. portion of the equation. So if we look here, the poles are just going to be, poles are just going to be 0 and -2. Any questions? Yeah. Oh, you want me to do that? Oh, I don't want. Okay, yeah, I'll do that. I'll do that. The question was, can I turn that ODE into an A matrix? Sure. The reason I don't want to do it is because I don't have notes for it, but I guess you really put me on the spot here. Anyway, so let's define it like this. Actually, I'm not exactly sure what this 1 will do to the ODE, but let's give it a try. X double dot is equal to -2x -1 plus 2u dot. And we do x dot is equal to ax plus bu. Then we get basically x dot, x double dot is equal to 0, 1. And then actually it's the x dot. And 0 -2, that's not good. Those are linearly dependent. Plus 0, 0, u. Okay, so in this case, we don't include these terms in our state space equation. And there's going to be when I do formulate this equation, we're only going to see this. When I use state space to transfer function of A, B, C, D. Actually, let me be careful about how I say that. Okay, well, this is our A matrix, okay? Let's just do this first. Determinant of Si minus A, which is going to be S minus 1, 0, S plus 2 is equal to S squared plus 2S, which is equal to S plus 2, which is equal to 0. Same thing. Note that the blue highlighted isn't part of our state equation, and it doesn't affect it because it's going to pop up in other terms. In this case, the blue term these are going to pop up in the C and D matrices. And I don't have this off of the top of my head, but yeah. Questions? Yeah. Oh yeah, I'm missing that. Yeah, thanks. I'm just making mistakes today. All right. Next week I'll bring candy and I'll throw candy at you guys for correcting my mistakes in spirit of Halloween. But yeah, that's how you find it. Whenever you don't have terms to put the blue terms, I wouldn't worry about that right now. Just formulate your A matrix because all the A matrix cares about is how the state variables are related to each other. It doesn't care about the derivative of the input or some constant being added on. Okay. Yeah.
Becoming equal to -2x dot, there is no input term coming. There is 2 times of u dot.
Yes.
Of state space, you have kept both of them as 0.
Yeah, because this is for the input and not the derivative of the input. The way the derivative of the input shows up is it's going to be formulated in the C and D matrices. And not remember off the top of my head what the formulation looks like. There's a section in the textbook that kind of derives why it acts like that. And I don't exactly remember off the top of my head why. Yeah. for now, when you see this, just use the Laplace transform. But yeah, if I were to be complete, I would say it would just be 0 to u dot plus 0 minus 1. But then these are just terms that are not part of the state equation. And at the end of the day, the poles are only dependent on the A matrix. Like by matrix, you mean like, yeah, so like these terms will somehow pop into the C and D matrices. Yeah. This part probably won't even pop up in the ABCD matrix. This is going to be like our initial condition term, basically. Yeah. Okay. So this is a recap of basically chapter 4.10. So basically, if A is full rank, in other words, all rows of A are linearly independent, then you can determine the response of the system's response in the time or frequency domain. So this is finding the time domain and the frequency domain solution. The reason why A has to be full rank is because you have to take the inverse of A, or you have to do the eigenvalue decomposition, and yeah, so the inverse of A is not invertible if A is not full rank. Although now that I think about it, the SI minus A might be invertible. Let me think about that as well. Anyway, here are the time solutions. That's in chapter 10. So then now we're going to move on to first order systems. So first order system is just a first order in the time domain. It's just a first order differential equation, which can be expressed as a first order system. The response is the exponential decay or growth. Bacteria growth, like around a colony, kind of have a exponential growth when food and space is not a constraint. Most real things are decaying. You don't have something exponentially growing. There's no such thing as free energy. We're constrained by laws of physics and energy. So if I were to like take this chair, it's not a second order system because if I push it, there's no oscillation, and it just stops rolling. So friction here is my energy dissipator, and I applied an impulse input, which is just a hard shove. That's a exponential decay. Let's see. Why do I have 2 pages of demo? Okay. So if we were to look at that, I have a chair with wheels, and my input is f of t, and in this case, it's just a impulse input. I'm going to just have unity impulse, and we're tracking position. Actually, no. Actually, let's track velocity. And then counteracting my push is force of friction. So maybe I'll say F D for dynamic friction multiplied by V, or X dot in this case. And we're going to call this X dot is equal to V. So there's going to be FD multiplied by velocity instead. So now instead of defining X position as our state variable, we're going to define velocity as our state variable. So let's do the free body diagram. Sum of the forces is equal to mass times velocity. The derivative of velocity, which is acceleration. So going to be equal to minus your friction coefficient multiplied by your velocity because it's counteracting my push plus our input force F of t. So then we get mv dot is equal to minus F of d multiplied by v plus our impulse. Actually, we'll just keep it in terms of input defined. Then when I take the Laplace transform of this, and because my initial condition was 0, my initial velocity was 0 before I pushed it, then we get ms times v of s is equal to minus f of d v of s plus f of t. Then when I factorize it and I get velocity in the frequency domain as my output, and my input is force, I get ms plus f of d, and then I get 1 in the numerator multiplied by the input f of s. All right, this should be a f of s. Okay, so then my transfer function is going to be v of s divided by f of s is equal to, and I'm going to divide both sides by 1 over m, the top and bottom by 1 over m, because I want s by itself. I get 1 over m divided by s plus f of d over m. So this is my transfer function. And I have a pole at minus friction coefficient divided by mass. Friction coefficient is positive, and we can see here that the size of this pole is scaled based off of my friction coefficient and based off of my mass. Okay, so let's say f of s is equal to 5 units of force. Basically, this is going to be me applying 5 units of the Dirac impulse. So if I were to find the velocity, it's going to be this. V of s is equal to 5. One over m divided by s plus f of d over m multiplied by 5. And if I were to take the inverse Laplace transform of this, it's going to be, I'm going to pull out the constant, which is 5 over m, and then the inverse Laplace transform of s plus, let's say s plus f of d divided by m is just going to be e to the minus f of d divided by m t. And this is equal to my velocity. Just a little side note, I guess, where I got that as well. When you take the inverse Laplace transform of 1 over s plus a, you get e to the minus at. So that's where I got that property from here. Any questions? So it looks right. I pushed it. It was exponential decay. The fastest velocity was right after I pushed it. It reached its top speed. And then friction took away its energy, where the response probably looked like this. It's an exponential, it's a negative exponential decay. And this is V of t. And we have the response going like that to 0. You can see that the decay rate is dependent on the mass. And also my initial velocity as well. The heavier I am, the slower my initial velocity will be. The lighter you are, like if I'm pushing with the same number of units of force, but then I weigh heavier, then my initial velocity is going to be slower, but I also have a slower decay as well, which is interesting. So if you think about the intuition behind it, hopefully that makes sense. That's what makes first order systems very easy to understand. The next demo I have is actually for why do we try to get 1 over m in the transfer function? Okay, so the reason why we try to get 1 over m in the transfer function here is because we want this form here to apply this inverse Laplace transform. We need s by itself. So that's why we have to divide. We have to get rid of this m. So we like the highest order to be by itself. Yeah. The second demo I have, it's going to be on a continuous step input, but I think I'm going to skip it because it's similar to the first demo. What I'm going to do is I'll upload the notes for this derivation for continuous push. So for a continuous push, like a step input. And, before even deriving it, you don't even need to, you can know that's going to be a constant velocity, because if I'm just pushing this continuously, I'm overcoming the friction force, and it's moving at a constant speed. It's moving a little bit slower versus if I were to walk by myself, because I have to put energy into the system. So it's going to be an exponential decay to a steady state value instead. And I'll upload the derivation for it. But the response is going to look like this. We're going to have an exponential decay to a target steady state value. And I'm going to call this V of steady state, VSS. So that's my steady state value. It's going to decay like that. And this is still an exponential decay. You're just doing VSS minus, or this value here is going to be some value constant minus your exponential decay. And I'll derive that later. So yeah, so the reason why I'll derive that later is because I actually have this derivation for a generalized unit step input. So let's say this is G of S, and we have a unit step input of U of S. Then our output Y of S is equal to, let me write it here, Y of S over U of S. So our output over our input, Y of S is equal to B multiplied by S plus A multiplied by U of S, which is equal to B over S plus A multiplied by 1 over S. All right, so then we can rewrite this equation like this. We do partial fraction expansion. B over S times S plus A is equal to, it's going to be this first term here, K1 over S plus K2 over S plus A. To find K1, I'm not going to write out the full step. K1 is just going to be equal to the limit of S going to 0 of S multiplied by G of S. And that's going to be equal to B over A. And then K2 is going to be the limit as S goes to minus A of S plus A multiplied by G of S, which is going to be equal to minus B over A. So then we get this B over A over S minus B over A over S plus A is equal to our partial fraction expansion Y of S. And when we take the inverse Laplace transform of this whole thing, we get Y of t is equal to B over A minus B over A e to the minus AT. So the output response is going to be equal to B over A multiplied by 1 minus e to the negative AT. So basically, so the derivation is a little bit fast, but it's just partial fraction expansion. There's a few notes about this. You can see that it's a steady state value. When I have a step input on a first order system, it's going to reach steady state value, assuming that the system's stable. I mean, all real systems that are first order are stable because you can't infinitely add energy and have it grow unbounded. We're going to hit a steady state value and scaled by B over A. And so then the way I think about this is this B over A is my system gain. Because if I put an input of 1 and my output is B over A, that's my gain. Because the gain is defined as the ratio of the output divided by the input. This here multiplied by the system gain is my steady state value. So actually, to be more precise, it'll be these two multiplied together is my steady state value. Because as time goes to infinity, this exponential term is going to decay. So then this is for when A is less than 0. And then this here, this exponential term is my transient response. Transient meaning that it's in motion. It's dependent on time, not in motion, it's dependent on time. Which makes sense because if I have a step input, I'm pushing my chair all the way down to the end of the hallway. Once I overcome that force of friction and we're at steady state, my velocity is constant, and that constant velocity is dependent on my system gain, which is B over A, which is how much I'm pushing into this system. Any questions? In this example here, A is going to be equal to force of friction divided by mass. Yeah.
Yeah, can you explain how you set up the
Yeah, I can explain that. So basically what we're saying is B over partial fraction notes. So we're saying that this over S plus A, and A and B are just any constants we want it to be, is going to be equal to K1 over S plus K2 over S plus A. Okay, so this is a linear equation, and I can rearrange this equation however I want. One thing to note is S can be any number I want it to be. It can be a complex number, it can be real. So this is the complex domain, meaning that it can be both complex and also can be real. And this equation will always hold true, no matter which values of S I choose. So basically what I'm doing is if I multiply both sides by S, So I multiply both sides by s. Basically, I'm saying b over s plus a is equal to k1 plus k2s over s plus a. Would you say that the first equation and the second equation are still the same? Are these the same equations? No, they're the same. Sorry. That's a trick question. It sounded like a trick question. It's not. They are the same equation because s is any number. S can be 5, s can be 10, s can be 0. So I multiply both sides by s, and then now I set s equal to 0. By doing that, I'll use a different color. This goes to 0, and this goes to 0. Now we're left with b over a is equal to k1. Because s is any number, because this equation always holds true for any s. So we're strategically choosing s to eliminate these variables. So I did the same with this right here, where when I set s is equal to minus a, I eliminate this k1 term because I multiply everything by s plus a. I guess since we only have 2 minutes left, I'll just do that because I don't really think it's worth moving on. So then I'll move this over. Exactly. So you use values of s strategically to make solving partial fraction expansions a lot easier. So now if I multiply everything by s plus a, then you get b over s is equal to k1 s plus a divided by s plus k2. And then when s is equal to minus a, this term becomes 0. I'll use purple now. That becomes 0. So this whole thing is 0. But then this becomes b over minus a is equal to k2. It's valid because s can be anything. And that's how you do that. And that's why people write this limit as s goes to 0. I don't know why they write limit as s goes to 0. We can just say s is equal to 0. But that's just the way I learned it when I was, or that's how the textbook has it too, I think. I remember learning it once. Anyway, it's 11:20, so let's call it for today. Tomorrow we're going to wrap up first order systems, and then we're going to go to second order systems. Thank you. And office hours are going to be online only today as an extra reminder.